So I thought I'd talk about the random functions that I built some while ago. So let's first talk about the existing or the old function generators that come with Quickcheck. So there are generators to generate a function that takes one argument or two arguments or three arguments, but they're a bit awkward to use. So I mean, it's a function, so you can't really see what it's doing, which is a bit annoying. Well, you can work around that, right? You have the function. You can just call it on some interesting arguments, and then you'll see what it's doing. So you do something like this. Right? You generate a random function, and then when your test fails, you just print argument and result pairs for some interesting arguments. And I mean, it's kind of clunky and annoying, but it sort of works. And the other thing it doesn't do, it doesn't shrink anything. So it's not shrinking the result values to the function, for instance. But you can kind of work around that as well. You can just represent, instead of using the function generator, you could generate a lookup table and turn that into a function. But that's also a bit annoying to work with. So you could do this, right? Say, well, my function generator generates a lookup table and then returns the function where you look up the thing in the table. And it kind of works. But we do some shrinking? Yeah, so now, I mean, you're just generating a list of pairs, and then that would shrink just using normal Quickcheck built-in shrinking. So you can do it. It's a bit clunky. But of course, this all relies on you knowing what the interesting arguments are. If you're up here, you've generated a random function, and you don't really know how your system, the function that you're passing it to, you don't know what it's doing with your function. Then you don't know what the interesting values up here are. And then this doesn't work. Or down here, if you don't know what arguments it's going to be called at, then you don't know what x's to put in your lookup table. So it'd be nicer to have function generators that would fix this. So Kuhn Klassen gave a talk. So in Haskell Quickcheck, he implemented printable, shrinkable functions a couple of years ago, and I went to the talk, and it was super cool. And I wanted this for Erlang Quickcheck as well. Of course, in Erlang, you have to do things very differently from the way you do things in Haskell of types. Right? So Kuhn's functions were type-based. So it looked at the argument, the type of the argument to the function, and based on that type, did some trickery. And in Erlang, that function, it just takes some Erlang term, and it could be anything. So I'm going to talk about exactly how these functions work in a bit, but first, let's look at some silly examples I made up. Okay, so here's a property that we would probably expect to be true. So what does it say? So it's testing the interaction between map and member. So it says if you so we generate some lists and some element and a function, and then when you map the function over the list, then f of x is not in the result. Then it should not be the case that x is in the original list. Because if x is in the original list, then you map f over x's, then clearly f of x is in the result of the mapping, clearly. So let's just make sure that that's the case. Okay. Yeah, seems to work. run it for a bit longer, just to make sure. I think Jesper might recognize this thing.
Yes, that's a good one.
Yeah, what? So if you have, so we got the list -0 and the element +0, then in fact it is true that +0 is a member of the list -0. But if you have a function that maps -0 to 1 and anything else to 0, then this list will map to 1 and x will map to 0, and it's no longer a member.
So you had two dots in the property.
Yeah.
Couldn't you just remove them both and swap them?
Yeah, I could, but then I get a lot more. I mean, yeah, it would work. You get a lot more x's because you have to generate. I mean, you'd be testing the same thing, I guess. It's just it would look. Yeah, it's equivalent. Yeah, you have to discard a lot more, and then it might give up. But on the other hand, a lot of the dots here are maybe uninteresting. Well, you could, and I tried, and it still finds it. It just prints more x's. So that's fun. And I mean, what's the so you can tell positive and -0 apart by using term to binary, because they have the IEEE representation is different. You can't tell them apart using match equality. So actually, this is a lie, right? It doesn't. If you try to write this, it will map +0 to 1 as well, because you can't match on that. But my functions don't know that. I mean, I'll talk about what they actually do later on. Okay, so here's an example I called silly. So it says if you have this is the well-known property that if you have a function on English words to natural numbers, or you have a function, right, and you generate two random words that are not the same, then if you add up the function applied to the word, which is an atom, I believe, and you apply it to the string, the corresponding string, then that's going to be even, for at least one of the words. So of course, it's not. What is it? You don't believe that? Yeah, it's not true. It's just. So here's the counterexample. If the two words are explorer and republic, and you map the atom to 1 and everything else to 0, then indeed, if you add explorer and the string explorer, you get 1, and the same for you can do. So that's a version where you map the string versions to. So this is a very contrived example just to show you what it looks like when you shrink the functions. Mr. Schott. Yes, no, I don't shrink the words. And also they're sorted by the frequency and representative English text, so you'd be the and a.
Why doesn't it shrink to 1 and 1?
That's a good question, actually. I mean, it can't shrink to 2, so I don't know. 3 probably shrinks to 0 or 2, but not to 1. And so it doesn't 3 doesn't in one step shrink to 1, my guess.
Throw it a double shrink.
Then it should work. Anyway, let's look at my last example, which is a bit more substantial. So this is a version of the game Nim. So the game is, you've got a set of things. Typically, you have multiple piles of little stones or matchsticks or whatever. In this case, I only have one pile. And each player takes turn to remove, in my version, either 2 or 3 items from the stack. And then the player that cannot make a legal move loses. So if you're a winning move would be to make sure there's 0 or 1 things left, because then the other player couldn't make a move. And here's the little function that runs a play. So a strategy is a function from the number of matchsticks in the pile to a move, which is going to be take 2 or take 3. And I should really check that K is 2 or 3 here. So you can't cheat, but I'll be careful not to cheat.
So here a player loses if they try to make it illegal.
Yeah. Well, I mean, so a strategy is a function from n to a move or to something, right? And so if you give an 0 here, you have to return something, and well, you could.
But if n is 2, then you can win. However, your strategy might choose take 3.
Yeah, and then you lose, because that's not a valid move if there's 2 things in the pile. So if you make illegal moves, then you also lose. You could try to take all of the things, and then you also lose. Okay, so I wrote a little property here that takes a number saying how many matchsticks do we start with, and then it takes a strategy and it tests that this is in fact the winning strategy. So how does it do that? Well, it generates a random strategy. So a strategy, as you saw up here, is just a function that returns a move. So, and then the property says if you play the strategy you feed in against this random strategy, then this guy wins. So play returns. You tag the strategies with a name and it returns the winner. So we run that. And let's say 19. It's good.
You have to come up with a suggestion for a winning strategy.
Yeah, so now we're saying, I believe, I'm pretty sure that this is the winning strategy, right? So if you just always take 2, then you're going to win. And we're playing the first player. And it says, no, in fact, you will lose. And you will lose to this strategy here, which if there are 13 things in the pile, it'll take 3. And when it gets down to 4, it'll also take 3. And then my strategy will lose. And then you could try to actually come up with the winning strategy.
So you can give this strategy as the winning strategy.
And then you can give this strategy. Yeah, we could. And then, well, okay, let's do that. That's easy. Well, yeah. I'll just type it in. So 4, it'll take 3. And 13, it'll also take 3. Yeah, well, I could, I guess. It's in the shell. It's a bit annoying. It says no. In fact, that beats your strategy that I gave before, but it's not the best one. In fact, this one is better.
That strategy that they came up with works as the second player's strategy.
Oh, indeed. So, in fact, yeah.
We're talking about the starting players.
Yeah, indeed. So,
You need to come up with something that's immune to whatever strategy player.
so why don't we write a property that says there is in fact no winning strategy for the first player.
Now we're talking.
So how do we do that? Well, when is a strategy winning? Well, if we can run 500 tests of the prop winning without failing. For a specific end, right? I mean, clearly for different ends, there may or may not be a winning strategy. And in fact, for 19, we'll find out if there is one, but I believe so. And I call that prop losing, saying n is a losing state for the first player. And in fact, it's not. There is a winning strategy. Well, I mean, we're running 500 tests, so maybe it may or may not be a winning strategy, but I'm pretty sure that 500 is enough in this case, and there it is. And you can sit down with pen and paper and verify that this is in fact.
So brute force actually works.
Indeed. Well, I mean, if you crank up 19 to 35, then it doesn't work anymore. But I mean, this is. You have to run a lot more tests. Indeed. Okay. Anyway, so that was a bit of fun I had, and it's, I mean, in this case, of course, you could do a table. You've got, the number of matchsticks only goes down, so you could just generate a lookup table of the moves, and that would work as well. They're quite convenient to use the functions. Okay, so how does this actually work? And so the Haskell version used some type-based trickery to generate the functions, and in Erlang we can't really do that because there are no types. So my idea was, why don't we represent the function as an infinite binary tree? Because everything that has infinite in it is good. So like this, right? So you have that this goes on forever, and in each node you store a random value, a random result, and then how do you apply a function represented as an infinite binary tree to an argument? Well, we have term to binary. Anything you could feed to an Erlang function, you can run term to binary on and get a binary. So you've got a string of bits, and then you just use that to navigate this tree until you run out of bits, and then you look at that node and you pick the random value that's stored at that position, and that's your result. And that guarantees that if you call the function multiple times, you'll get the same value every time, because the tree doesn't change. I mean, it's a fixed tree for.
So when you generate the tree, you're telling what type of stuff you store in the nodes.
Yeah, so I mean, just like the existing function generators, they take an argument saying this is the Quickcheck generator used to generate results. So in each node, you use the generator to generate a value to go in that node. And then since it's infinite, you have to kind of take care not to generate the whole tree at once, because that would take a long time, I think. But so you have to do it lazily and just generate it on demand. So what about shrinking then? So we wanted functions that were shrinking and that we could print. So in the examples, it said for this value it gives you this, and for this value it gives you this. So we need to be able to take this infinite binary tree and throw away stuff. In particular, it'd be nice if once we've shrunk it, it's no longer infinite but finite. And the idea is, well, why don't we just prune the tree? So you just snip off branches, saying, well, a possible shrinking step is to just take out that subtree. But then, of course, what happens if you're actually trying to apply it to something that lives down here? And the trick is to just have an extra value, which is the default, the catch-all clause, as you saw in the counterexamples. All the functions had a catch-all. If it's anything else, then this thing. So we just we add on beside the tree a value to use when you're looking in something you've thrown away. And then once we've snipped off enough branches so that we have a finite tree, then we can actually turn the tree into a lookup table. Because once they're, it's a finite tree, then there are a finite number of nodes, and you could just enumerate all the nodes. So you do this instead. And I'm hoping, I haven't found a counterexample. I think that term to binary is prefix free. I'm hoping that's the case, because otherwise but I tried to find a case where it wasn't, and I haven't managed to. I think it's true, because and you can sort of argue for why it would be the case, because a lot of the time when you're storing something of variable length, you store the length as the first byte, so that would give you. So this means that you can throw away, if you have one node down here that you need, you can shrink away, then all the nodes on the path you can ignore. And that works quite well. And then once we have this, we can print this by just turning these binaries into binary to term to print what the actual argument is. And that worked quite well. And oh yeah, we also want to shrink these values, of course. So we don't, and the way to do that is to not store just a single value in each node, but you store a value together with all the shrinking steps for that value. So that works. But, well, I mean, it wasn't too many orders of magnitude slower than the existing generators. But a few. More than one. Which is, I mean, so if you want to use this, it's nice if, calling the function is not super duper expensive. And perhaps, maybe not surprisingly, navigating a binary tree bit by bit is not going to be very fast. But there's some things you can do to fix that. So one thing is to observe that actually when you do term to binary, you get a whole number of bytes. You don't get something with 13 bits. You get something with 2 bytes in it. And so instead of a binary tree, we can use a 256-ary tree. So you just do this. That means that as you're traversing the tree, you do 1 byte at a time, and that saves a lot of time. And the other thing you can note is that once you start shrinking, you get very sparse trees. So a big win is when you get, so you're going to get a long sequence of bytes that goes down to a single node. So if you just compress branches like that, so you say, well, in this case, this turns out to be how I think integers start. And just do a single branch for this binary, then that saves a lot of time as well. And then the result is pretty good, I think. It's 9 times slower for the the initial functions you generate than the functions that you get from XCgen, which is fine. You have to pay a little bit to get the nice shrinking, not too much. Once you've shrunk it, of course, it can be a lot faster because it might shrink down to the constant function that doesn't look at the argument at all and just gives the result. And if it's got a couple of choices, then it's a lookup table. It just looks at the time to binary, so it can be faster. What's the time?
48.
What does it mean? I'm 3 minutes over. Okay, good. So let's do this slide and then this is second to last slide. So another nice thing about this, which I didn't think of at first, but which I realized when I'd implemented it. So we put, at every node in the tree, we use the generator you pass in to generate a value for that node. But in that position, we actually know what the argument is. So we could allow the generator access to that argument. So looking at, you can see fun, you also have generators which take with 2 arguments. And this is not, I've simplified the type syntax here. So it takes, this is the result generator. It gets to look at the argument before deciding how to generate a value. But then you also have to pass in a generator for the default, for the catch-all clause, where you don't have access to the argument value. And then it produces a generator for function from A to B. So that's quite nice if you want to generate a function that has some constraints on the type of thing that it should produce given what the result is. So you can imagine in my little nim game, if n is 2, then it shouldn't generate take 3, because that's stupid. And you could do this with this dependent generator. Right. 5 bubbles. Okay, so go test your higher order functions, or if you don't have any higher order functions, write some and then test them. Thank you.
Excellent.